Hi everybody. It's time to do a few work and energy example problems. These should be review. We did a note organizer in class. I'll show you what that looks like. Looks like this one here. Maybe a little different. Yours might look a little different, a little more updated. And these problems back here. And so this is kind of a continuation of that stuff. All right. Here's what we'll do. I will kind of get you started on some of these and have you finish them. And some of them I'll do all the way through. Okay. Now notice that when we get to the back here, this is brand new stuff. And we're not going to do this in class. So make sure, especially, this is probably the most important part. This is kind of review, the rest of it, but we still need to really focus here as well to kind of solidify these concepts of conservation of energy. Okay, so we'll start out with example 4 here, and it's just simply a kinetic energy calculation. Okay, so we have a baseball, 145 grams, and we've got its speed. What is the kinetic energy? All right, so Ke is equal to 1/2 mv squared. Only thing that's tricky here is we need to pay attention to units. All right, that is going to need to be converted to kilograms. So we'll say 0.145, 3 decimal places. And another common mistake is not squaring your speed. Alright, so make sure you square the 25 there. And if we punch that into our calculator, we will get what? Let's do it. 0.5 times 0.145 times 25 squared. So we get 45.3 joules. We'll round that to just 45 joules. Second part of this asks us about work. How much work is done on the ball to make it reach this speed? Okay, so we know that if we do work, we can get kinetic energy. Okay, or if we do work, we can also change something's potential. Okay, now this is very important. A lot of times when people see work, they say, oh, work is equal to force times distance, and I got to have that to get that. Okay, there's another way to get work, and that is to look at what the kinetic energy did. Okay, so we have to remember that the net, okay, it's only the net work, okay, or the work done by the net force. Work net is equal to delta Ke, all right, or the change in kinetic energy. So if we take the final kinetic energy and we subtract the initial, we get the net work, okay? So this is a super easy problem because here's the final kinetic energy. The initial kinetic energy is 0 because it started from rest, okay? So we're going to just say the change in kinetic energy is 45 joules. And that's all we have to do. Okay, let's look at a couple problems with potential and kinetic, both involved. And I'll do this first one and then I'll have you guys do this second one. Maybe I'll throw in a couple hints on this. Okay? Alright, so here's what we've got going. We've got a dropped rock, very exciting. What is the stone speed when it has fallen to 1 meter above the ground? And it's starting at 3 meters. Okay, so here's what I'd like us to do anytime we have a conservation of energy problem. Energy initial equals energy final. Okay? Just writing this often gets you a point on AP problems. Okay? Now, there's some situations where this doesn't apply. Okay, like if they said, hey, there's a bunch of air friction in here, then we'd have to subtract out the work done by friction. Same with something like this. we really have to look at every single problem and say, hey, is the energy for this object actually conserved? All right, and if it's not, then we're subtracting out some joules lost to friction a lot of times. Here, we are going to assume this is a frictionless situation. They didn't say anything about air friction or anything like that. Okay, so here's what we can do. We can say the potential energy initial plus the kinetic energy initial is equal to the potential energy final plus the kinetic energy final. All right. Now there's a way to shortcut in this problem as well. Okay, and I'll show you that at the end, but sometimes it's a good idea for us to lay out the whole situation like this. Okay, so initially, do we have any kinetic energy? We do not, so this is going to go to 0. We have potential to start, okay, and then right here is where we're a meter above the ground. This is 3, this is 1, okay, 2 meters is right in there. So we have potential to start, and then at this point we have kinetic and potential energy. Okay, so we're going to have both of these terms, and we haven't done any problems like that so far. Okay, so here's what we're going to do. We're going to say mgh1 is equal to mgh2 plus 1/2 mv squared at point 2. Okay, now if there's an m in every term, we can cancel it, so we'll get rid of all the m's. All right, and I'm just going to plug in the numbers and solve. Plug and chug. That's okay to do sometimes. So here we've got 9.8 times height 1, which is 3 meters, equals 9.8 times height 2, which is 1 meter, plus 1/2 v2 squared. Okay. All right. And so we're going to have to multiply and then subtract a 9.8 over to this other side. So it's going to be 19.6 equals 1/2 v2 squared. Okay. And that would be 3 9.8s minus 1 9.8 is a 19.6. Okay, then we're going to multiply that by 2 and square root it. Okay, and if you do that, you should get 6.3. So type that in yourself. And V2 equals 6.3 meters per second. Okay, so that's going to be the velocity not at the ground, but the velocity midway through. Most of the problems we've done so far have started here and ended here. Okay, turning potential all into kinetic. But here we've got potential in the middle too. So that's how we deal with situations like this. Okay, let's look at the next one. Got a roller coaster here. And we've got a 40-meter hill. The roller coaster is going to start from rest at the top. Okay. And they ask us about 2 points here, A and B. So I like to kind of label on my diagram. I could call this point A, I could call it point Z, I could call it whatever. I'm going to call it point 1. Here's point 2. And then they're also going to ask us about another point in part B down here. So I'm going to call that point 3. Okay, speed of the roller coaster at the bottom of the hill. So this height right here is our 40. Okay, and first they want to know speed down there. Okay, that's an easy problem. Let's set it up. EI equals EF. Okay, I want you to decide what type of energy we have here and what it's going to. All right, and solve for the speed. Need to show your work. Okay, part B. At what height will it have half of its speed? Okay, so you're going to take the speed from here, half of this speed, sorry. You're going to take the speed you get here, divide it by 2, okay, and that's going to be asking you about the speed at, that's going to be the speed at point 3, and you're going to have to find the height at point 3. Okay, so I'm going to help you guys in setting this one up. EI equals EF. And what I want you to do is, using point 1, potential energy at 1, plus kinetic energy at point 1, equals potential energy at point 3 plus kinetic energy. Kinetic energy at point 3. Okay, so decide what types of energy you have here. Decide what types of energy you have when it is at half of its speed, half of its final speed from here. Okay, and you're going to solve for not PE3 but the height here. We already have the height here. Okay, so see if you can reason through that, and I'll check your answers to this and this in class. Okay, on to the other side. This is a great problem right here. Okay, and if you've ever been to Waterworld in Denver, they have these slides, alright, and they're super fun. So Paul and Kathleen are going to race. Paul's slide is shaped like this. Kathleen's slide drops fast at first, but then shaped like that. And they're going to ask you two things. Which rider is traveling faster at the bottom? Alright. And then which one makes it to the bottom first? Interesting. Okay. I want you to write your answers and also justify them. You don't have to write a paragraph, but explain in words why. If you just do one words, no credit on that one when we check this in class. Okay. See what you think. Example 11. Estimate the kinetic energy and the speed required for a 70 kilogram pole vaulter to pass over the bar. And we're going to assume the pole vaulter's center of mass is already 0.9 meters off the ground. Okay, let's draw a picture of this one. We've got this bar up here. Here's ground level. Alright, and then the person's center of mass is 0.9 meters off the ground already. So here's the person. Center of mass is roughly in your chest. Okay. So this is already 0.9 right here, and they need to get up to 5 meters up there. Okay, so they want the what do they want here? Oh, estimate the kinetic energy and the speed. Okay, so they want us to calculate the kinetic energy and the speed at launch point for them to make it over. Okay, so again, I want you to set this up. EI equals EF. Okay, and decide what types of energy they have to start. Okay, when they launch, and by the way, they do have kinetic and potential at launch, and then decide what they have at the top. It's just potential. Okay, and you know what? Let me throw out the answers to this one so you can work through it and check your work. Okay, so their speed for takeoff needs to be 8.96 meters per second. And their kinetic energy is equal to 2810 joules. Okay, and you could get this first and then get this, or you could get this first and then get that. Alright, So kind of two ways to solve that. All right, so in here you need to work this problem until you get those two answers. Okay, that's all review stuff. Work through that. Going to need to pause it a bunch of times and try it out. Okay, now this is new stuff. Let's go over some brand new energy stuff. Okay, what is mechanical energy? Mechanical energy is potential and kinetic. Okay, so you already know gravitational potential. There's only one type of kinetic, that's just energy of moving stuff. But there's also another type of potential that we will deal with, and that is spring potential. Okay, all of these things are mechanical energy. All right, what is not mechanical energy? Heat is not mechanical energy. The work done by friction, okay, creates heat. That is not mechanical energy. Okay, but these three types are our mechanicals. All right, so here's what we got going. When we load up a spring, it makes sense that that spring now has potential energy. Okay, so elastic potential energy, a spring or other elastic object like a rubber band, has potential energy when compressed or stretched, because when released it can do work. That's why they call it potential. It has the potential to do work. Okay, so this again applies when compressed or stretched, either way. Okay, now you already know this. You already know F equals K delta X. That's Hooke's law. Okay, that tells us what happens when we what's happening with force when we compress or stretch something. We have that down here. Okay, now we're going to deal with this with energy as well. Let's start with the graph. And this is going to be sort of review to start. Okay, so let's say we're going to compress or stretch a spring. And we're going to put the force here and are changing X over here. Okay, so we could have these different springs. All right, let's say the first one, if we stretch it this far, it takes that much force. Let's say we got another spring, and if we stretch it the same distance, it takes that much force. Okay, and yet another spring. Okay, so we could have all these different slopes. What does that slope represent? Okay, you should know very well by now that that slope represents K. All right, the spring constant. So this would be a light spring. This would be a tough spring, or a strong spring, or a heavy spring, like a shock absorber or something like that. Okay, and for any graph you are given, you should be able to analyze the slope in the area. So let's analyze this slope, and we always just go back to what our math teacher taught us. Slope is rise over run, and then we start thinking about what these things represent. Okay, so the rise, that is Fs. The run is delta X. Okay, and then I like to look at units. Force is in newtons. Spring is, or the delta X is meters. So that's newtons per meter. Okay, and we know that newtons per meter is K. All right, that's the spring constant. Cool. Okay, we already know that stuff. And then we say Fs is equal to K delta X. All right, now very important, anytime we deal with a graph and an equation, we should be able to take that equation and put it into y equals mx form and kind of compare. So look at this. This is our y, this is our m, and this is our x value. Okay, very easy. This is the easiest linearization you've ever done. Okay, it doesn't have a plus b. because if we don't have any delta x, if delta x is 0, there's no force on the spring. So there's no plus b in this equation. Okay? All right, so we've already done that before. That's good review there on Hooke's law. And you even did a lab on that. Okay, so now let's deal with the same graph, but deal with the energy. So we're going to redraw it. Here's delta x. Here's the force on the spring. And we've got some spring slope like that. We already know what slope means. Okay, slope equals k. All right, now what about the area? Let's look at the area under the graph here. Okay, I'll switch to red G2. Area is equal to a base times a height. Okay, this is a triangle here. All right, I know that it's actually 1/2 base times height. Okay, but what I would like to do is take a look at just a snapshot of the area under here just to analyze the units. Okay, so let's look at that. Let's take a little chunk out of this. Take a look at the area. Okay, so the base, we're going to say that the base is x. Okay, the height is force of the spring. Okay, so I've got a force times a distance. Okay, so I've got meters times newtons. Okay, or newtons times meters. All right, so the area represent what? Okay, here it's newtons over meters. Here it's newtons times meters. What is that? Okay, N times M is equal to joules, which is equal to work. Work or energy. Okay, so it makes sense. We're exerting a force here over a distance. If we're compressing this or stretching it, we're using a force over a distance. Okay, now the problem is the force keeps changing the whole time. Okay, if we look at this graph, it's not a flat line. If it was a flat line, it would be really easy to get the work. Okay, we're going to actually have to do another step because this is not a flat line, but it's still easy. Okay, so what if we want the total area under here? Let's look at this whole thing. By the way, in calculus, this is an integral. Okay, so total area all right, instead of just looking at a snapshot here, total area is 1/2 base times height. Okay, this is a triangle. So we're going to say A equals 1/2. The base is x. Okay, or we could say delta x if we wanted to. Times the height, which is whatever force is on the spring. And notice that force keeps changing. Okay, we're going to be looking at the maximum force there. All right. And then we're going to do this. We are going to say, okay, well, from up here, we know that the force is actually k delta x. So I'm going to take this right here, and I'm going to sub it in right there. So area is equal to 1/2 x times kx. I'm going to leave the delta out. Okay, and I just subbed in Hooke's law for force of the spring. Okay, let's clean this up. Area equals 1/2 k x squared, or k delta x squared. All right, now what is this? This is the work done, because we said over here the area is the work. This is the work done to compress or stretch a spring. Okay, and if we do work, we now have this potential energy in the spring. So